relativity, quantum computing, and his blog is also very well known. I truly recommend him. And it's a pleasure to have him here also because it's a joint event between our first joint workshop between the Institute of Mathematics and Institute of Philosophy, and also the series of talks of the Institute of Mathematics with the Facultad de Ciencias of Perspectivas Matemáticas. So let us welcome.
All right. Well, thank you so much, Sergio. It's wonderful to be here. Unfortunately, I just realized this morning that this talk does not really give a general introduction to quantum computing. Now, my talk tomorrow morning will give a general introduction to quantum computing. So if you have exactly, it's a backward proof, or more in my language, if you have a closed time-like curve, then it could all make more sense to you. Okay. But I will try to include explanatory comments. But fortunately, this talk does not require a lot of technical knowledge. Certainly, not about quantum mechanics. We can just assume certain things, and then we'll be sort of talking at a higher level about what you can do with it, and actually what people are hoping to do. Even in the very near future, meaning the next 2 or 3 years. Okay, so it's which brings me to my topic. It's a very exciting time for quantum computing right now because of the very near-term prospect of achieving something that's been saddled with a very unfortunate name of quantum supremacy. This term was coined by my friend, the physicist John Preskill, in 2012. Now, this was before the rise of Trump. This was before this word supremacy, I guess, reacquired all of these disturbing connotations. But now people debate about changing the name. One proposal is to call it quantum inimitability, as in inability to imitate with a classical computer. If you can pronounce that, you're welcome to use it. Another suggestion is to call it quantum ascendancy. But that sounds too much to me like we're some UFO cult, ascending to a quantum computer in the sky or something. But what do people mean by this term? I should say, so in this talk, I'm going to talk about some of my work on the foundations of quantum supremacy, which is from a year ago and is joint with Li-Ji Chen, who is now a grad student at MIT, was then an undergrad at Tsinghua. And then in the second part of the talk, I'll talk about some brand new work from this year, which I haven't written up yet. Okay, so what do people mean by this term? Well, basically, they just mean, doing anything with a quantum computer that we can be very confident is difficult to simulate with a classical computer. Okay, so we're not asking to do anything useful. We're setting the setting the bar a little lower, right? You don't have to break any cryptographic codes. Don't have to read anybody's email. Don't have to simulate any commercially useful molecule or any of the other applications that people hope to someday be able to get from quantum computers. All you need to do is something that is classically hard, okay? Could be completely useless, okay? And that, but that we can be confident is classically hard, okay? Now, for me personally, this has always been the #1 application of quantum computing since the beginning. Namely, more than breaking cryptography, more even than, simulating physics and chemistry. What I really care about is just refuting all these people who come to my blog and who leave these comments saying quantum computing is a fraud, it will never work, it's you just don't, haven't, I just thought about physics for 5 minutes and I figured out a devastating objection why it can never be built, and that hasn't occurred to any of you, and I want these people to have to admit that actually quantum mechanics was a profoundly true account of the world. Okay, and if and if quantum mechanics works, the way that it seems to have worked for the last 90 years, then I think it's very hard to understand why you could not someday build a quantum computer, right? If you could, either there would have to be a problem with quantum mechanics, or else there would have to be something new on top of quantum mechanics that somehow censors quantum computation or somehow prevents it from working. But either way, I feel like that would be a revolution in physics, right? A discovery that quantum computing can never work would actually be much more exciting scientifically than a mere success in building a quantum computer. That would be the more boring outcome, okay? Now, my own bet, I guess being scientifically conservative, I bet on the more boring outcome, right? I think, yes, eventually it should be possible. That doesn't tell us how long it will take, how much money it will cost, anything like that. But, I see no fundamental obstruction, okay? But either way, well, we would like to learn the truth. I think it's a profound scientific quest. Okay, so I named Gil Kalai, who's one particular skeptic. Okay, but Leonid Levin, who you may have heard of from as a co-founder of NP Completeness, he's another famous skeptic of quantum computing. There are a few physicists who are. I would like to know the truth. And what's exciting is that in the next few years, there is a race right now among several players. Maybe the best known is Google, also IBM, also Intel, also a startup. Microsoft is sort of taking a longer term approach. Okay, so they're not exactly in this particular race, right? They're trying to build topological qubits, which would take a lot longer. Okay, but in this near-term race, also a startup called Rigetti, also University of Maryland, are sort of racing right now to build quantum computers with about 50 to 70 qubits. And I mean sort of good qubits that behave well enough to see a quantum speed up. You may have heard there's this company D-Wave that has 2,000 qubits. I'm not putting them in this category of good qubits. Okay, so we want qubits that can actually maintain their quantum state for a long enough time that the device can do something that is hard to simulate using a classical computer. Right, that's the goal. That's been the goal all along since Richard Feynman proposed the idea of quantum computing in the 1980s. Okay, but now it is sort of only now within the last few years that I think the technology has advanced to the point where sort of scaling up, even starts to make sense. Okay, and that's happening mostly in two platforms. One is superconducting qubits, which is what Google and IBM and Rigetti and Intel are doing, and the other is trapped ions, which is what NIST and University of Maryland and some other players are using. Okay, and there are some other approaches like optical qubits that are being pursued elsewhere. But Google in particular has set a clear goal of passing this milestone of quantum supremacy, just doing something that is sort of would be, on a fully programmable quantum computer, a small one, and one, without error correction, meaning, it's, you're sort of fundamentally limited in how many qubits you can deal with. So there will only be, let's say, I think in the chip that they're building now, which they call bristlecone, it's 72 qubits. Probably not all of which will work reliably. So let's say 60 qubits. Okay, but they hope will be enough to do something that would, we're pretty confident, would take 2 to the 60th time or something like that to simulate using classical computers, which you can do just barely, at least if you're Google and you have access to, an enormous cloud resources, but, it is quite expensive, and you could very clearly see the gap and see that the quantum chip was doing something much, much faster. Okay, so I think, this will be a huge scientific milestone for the field when and if it's achieved. Okay, but it is also, you know, for me personally, right, I mean, since I've been in this field, quantum computing, there have been theorists and there have been experimentalists who have sort of been on two separate tracks, right? And it is only very recently that, you know, the most hard-nosed experimentalists, such as the group of John Martinez at Google, are now coming to complexity theorists, of all people. And they're saying, well, you know, once we get our chip working, what should we do with it, right? You know, and what should we do that, you know, you are willing to sign off is hard to simulate with a classical computer, right? And is actually going to demonstrate a separation, right? And how should we prove that we did it? Okay, so you know. So now, we have things that actually, you know, and they raise all sorts of things for us that actually would be super interesting, even as purely theoretical questions, even if they weren't going to feed into these experiments that people are now trying to do. Okay, so that's sort of the backdrop for this talk. And so what I want to talk about is basically what should Google and the others be doing that we are as confident as possible is hard to simulate classically. How do we know that it's hard to simulate, or on what grounds can we argue for such a conclusion, right? How do we rule out that a classical computer could also do the thing equally fast? I mean, doesn't this bring us into the domain of questions like P versus NP, which I talked about yesterday? Okay, well, indeed it does. You know, we will have to make some sort of assumptions about computational hardness in order to argue that these tasks are hard for a classical computer. Obviously, what we would like is for those assumptions to be as weak or as believable as possible. Okay, so, and then in the second part of the talk, I'll talk about, well, once Google achieves this, or someone else achieves this with 50 or 60 or 70 qubits, is there then immediately something that you could do with it? Okay, and for years I would give talks about quantum supremacy experiments, just sort of basking in the uselessness of this task, right? Obviously, this is not going to, help anybody to just prove the quantum. It's just going to prove the quantum computer's strength. Okay, just like, people thought for, we've heard of the Bell inequality, right? People thought for decades, obviously, that has zero applications to anything, okay? It is only just to prove the reality of quantum entanglement in our universe and to prove that Einstein was wrong when he, rejected the spooky action at a distance, okay? Except, as I'll explain, over the last decade, people realized that the Bell inequality does have applications. Okay, and these experiments can actually be used, for example, to generate cryptographically certified random bits. Okay, and what I'm going to talk about is that these quantum supremacy experiments could likewise be used to generate cryptographically certified random bits in a different way. Okay, and a way that would be more suited to sort of distributing certified random numbers over the internet. Okay, and so this is actually now an application that Google is moving forward with and that they're going to try to implement. Okay, it's probably the first thing that I've done in my career that has even a risk of being useful to somebody. Okay, so that's sort of exciting to me, and I'll be happy to tell you about that as well. Okay, but now let me go back to 2011 or so, okay, when some of us were thinking about this topic already, and some of us, just independently of each other, came to I think a key realization, which is that if your goal is just to do something with a quantum computer that is hard to simulate with a classical computer, right, then there are a lot of advantages to sort of switching attention to sort of, let's say, broadening your notion of a computational problem, okay? So, the most famous thing that quantum computers are known to be able to do quickly is factoring huge numbers, okay? That's the famous Shor's algorithm from a quarter century ago, okay? But now, that's very impressive, right? But there are sort of two drawbacks to it, if you like. The first is that to actually realize Shor's algorithm seems to require building a full fault-tolerant quantum computer, and once you include all the error correction, you could be talking about millions of physical qubits in order to just factor a number with, say, 1,024 bits. Okay, so, yes, it's possible. Maybe there will be some Manhattan project, someone will spend $1 trillion, or maybe someone will have, a new idea that will cut down the cost by some orders of magnitude. Okay, but that is not something that's going to happen in the near future. I don't think, not in the next 5 to 10 years. Okay, but if you just want to do anything that is hard for a classical computer, well, then that may be much easier. You may be able to do that with a much sort of more limited type of device. And then a second issue is that mathematicians are not actually confident that factoring is a classically hard problem. Okay, I mean, we believe that enough that, we base the security of most of the world's e-commerce on that belief. But, what I like to say is, if someone tomorrow announced a fast classical factoring algorithm, so yeah, that might collapse a lot of the world's economy, okay? But, to me, collapsing the world's economy is just not that impressive as a complexity theorist. I mean, we in the U.S. are, working hard to do that, by more mundane means, okay? So, what's more impressive to me as a computer scientist would be to collapse the polynomial hierarchy, right? Or to otherwise sort of change the whole structure of complexity classes that we think is there. Now, a fast classical factoring algorithm would not do that because factoring is not believed to be NP complete, right? It's just this one specific problem. Okay, but what we realized is that for other problems, you can actually relate the non-existence of a fast classical algorithm for them to very, very generic beliefs in complexity theory, including that the polynomial hierarchy is infinite, right? Which is just like a generalization of, our sort of core belief that P is not equal to NP, okay? So in order to get all these advantages, what we were sort of forced to do is to switch attention from decision problems, like the ones I talked about yesterday, for those who were there, or problems with a single right answer, like factoring, to sampling problems. Problems where your goal is to output a sample exactly or approximately from some desired probability distribution, right? So, so basically the quantum computer is just doing what quantum mechanics tends to do, which is generating samples from a distribution. And now the classical skeptic's challenge is now to quickly generate samples from that same distribution, basically, or something close to it. Okay, and so this realization that these sampling problems give you these advantages was made by me and Alex Arkhipov in our proposal we had called boson sampling, which was about how to do this using a linear optical quantum computer, where all you'd have to do is generate photons, send them through a network of beam splitters, and then measure where they end up, right? I mean, generating single photons reliably is the hard part here, okay? But this is still sort of much less than it would take to build a full universal quantum computer, right? Which was one thing that was interesting about it, that, that this already can do something that appears to be classically hard. Bremner, Joza, and Shepard had an analogous proposal with something called their commuting Hamiltonians model. Okay, and actually, there was even earlier work by Turhal and DiVincenzo that had sort of made this point, sort of, without connecting it to the collapse of the polynomial hierarchy. But I think that, they really deserve the credit as the first to think of this. Okay. So, well, the disadvantages Well, until very, very recently, I thought, okay, well, if we take this route, obviously we're giving up on any hope of a practical application, right? Nobody cares about solving sampling problems, except people who are just trying to prove that quantum computing works. But then also there's sort of an irony in all these proposals that verifying the results of the quantum computer will itself be an exponentially hard problem, as far as we know, right? So, for example, if you could solve these sampling problems with 1,000 qubits, well, your device might be working fine, but you could never prove it, okay? Not even with a second quantum computer, because that would just output some other samples. Okay, so these proposals are really specifically targeted to near-term quantum computers, like devices with 50 or 60 or 70 qubits, for which classical verification will be very, very difficult, but not impossible, right? So the classical computer can do the calculation to verify the results, but you will see that it takes much, much longer. Well, because with 20, you're basically dealing with a million floating point operations, which is still fast enough with a classical computer that, you're not even, it's like less than an eye blink. Okay, so, I would at least like the classical computer to have to break a sweat. Okay? Spend some days, you should at least need a cluster or something like that. Okay? Let's at least go out to the limits of what classical computers, can simulate, even if we can't go beyond those limits while still verifying the result. Okay, good. So, and that's sort of the reason why people have focused on this number of 50 or 60, right? Not that there's anything magical about it, just that, this is where the crossover seems to happen, where a classical computer is only barely able to keep up with the quantum computer. Okay, so the basic proposal that some of us suggested and that Google has sort of adopted as sort of its key experiment that that they're going to try to do in the next couple of years. Well, it's almost just the first thing that one might think of. We didn't think of anything better, okay? Which is simply, generate some random quantum circuits, meaning just random sequences of operations on, 1 or 2 qubits at a time. So, random pulse sequences or whatever. Then, fix those circuits, so remember what they are, okay? And then every such circuit, if you apply it to some standard initial state, like we usually take the all-zero state to be our standard initial state in quantum computing, then it will give rise to some quantum superposition over n-bit strings, where n is 50 or 60 or however many qubits you have. Okay, and then you can take that quantum superposition and you can measure it, right? Measurement in quantum mechanics takes your superposition and collapses it and returns a single classical string probabilistically as the outcome, right? As I'll explain tomorrow, one of the central rules in quantum mechanics is that the probability of seeing any given string is equal to the squared absolute value of the quantum mechanical amplitude of that string. Okay, so strings with higher amplitudes are more likely to be observed than strings with smaller amplitudes. Okay, but in any case, each quantum circuit gives rise to some particular probability distribution over n-bit strings, right? And so every time you run the circuit in your quantum computer, you can get another independent sample from that distribution. Okay, now in the Google design and in many of the others, the superconducting qubits would be arranged in a square array. Okay, and you can do arbitrary, so it's programmable, and you can do by using control electronics that come into the chip from the outside, you can do whatever sequence of 1 and 2 qubit quantum gates you would like, where each gate can act on nearest neighbors, right? So you could do, and you can do many operations in parallel, okay, on disjoint pairs of qubits. So you can do sequences of layers of gates that sort of look like that, Okay, so let's say it's a square root of n by square root of n grid of qubits, and so the depth of your circuit should at least be great enough that every qubit is able to influence every other one. So let's say at least square root of n or so. Okay, and and then all the known classical simulation methods start having trouble. Well, they start facing an exponential blowup. Okay, we'll come back later to exactly how good the best classical simulation methods are. Okay. So then we apply our circuit, the L0 state, we repeat some number of times to get independent samples. Okay, and then we need to, with our classical computer, we need to apply some statistical test to these samples, right? Because we don't observe the probabilities, right? All we observe is the samples. And now we need to somehow test whether these samples are plausible draws from this hard distribution, right? So to be clear, the distribution, the probability distribution is not going to be uniform. If it were uniform, well, that would be easy to sample with our classical computer. Okay, it will have little bumps in it, right? Some, because of constructive and destructive quantum interference between, different contributions to each amplitude, some probabilities will be larger, some will be smaller, right? They'll have, we actually understand what the distribution over probabilities looks like. I'll show you that in a later slide. Okay, so, but now, knowing the distribution, you have to check whether your samples are plausible draws from it. Okay, so Google has a test that they want to apply involving cross entropy. In our analysis, we prefer to use a different but closely related test, which we call heavy output generation, or HOG. Okay, and the HOG problem is basically just to output a collection of strings, a large fraction of which are assigned large probabilities by this distribution. Okay, by large I mean like at least 1 over 2 to the n, or like more than the median of all the probabilities, which will actually be natural log 2 over 2 to the n, I think. Okay, so to be clear, this is something that if you had a perfect quantum computer and you were correctly sampling, then that is something that you would do with overwhelming probability, right? With a classical computer, it seems like you would just be guessing randomly, right? You'd be shooting in the dark, and your probability of doing that seems a priori like it would be exponentially small, right? And we can check which one by actually calculating the relevant ideal probabilities with our classical computer. Okay? Admittedly, that takes 2 to the n time with our classical computer, but as I said, we're assuming n is small enough that we can do that. Okay? And then, you could publish the circuit, and you could challenge any skeptic. Well, then you try to, you don't believe us, then you try to generate samples from this distribution, right? Similar to what people do in applied cryptography, right? Where they publish a challenge problem and they, invite anyone to break it, okay? Now, we could just stop there, but as complexity theorists, we would like to go a little bit further than, I don't know, seems hard to us, okay? All right, so we do that. We give some hardness reduction. Okay, first, this is what the distribution of the probabilities looks like. The probabilities one can actually show are exponentially distributed random variables. Okay, for many ensembles of quantum circuits, that can actually now be, from recent work, be rigorously proven. And even for those for which it hasn't been proven, we know it to be true by way of MATLAB. Okay. What? Oh, so let's say the probability that you will, if you pick a string x, then and you look over all quantum circuits, then the probability that the probability of x is like at least b over 2 to the n. So say at least x over 2 to the n goes like e to the minus x. Okay, that's what I'm indicating here. Okay, but then that means that if you're doing sampling, then the distribution over probabilities of the things you observe actually looks like this. It's weighted because, you would never see anything that had probability 0, right? And, each string is actually weighted by the probability that you see that string. Okay, so you can, by inspection, right, this is different from this, right? So, so this is sort of the signal that you're looking for, okay? And this signal is something that the physicists call speckle, okay? It is very closely analogous to what happens if you take a laser pointer, like this one, and you put it through a bunch of ground glass. I don't have ground glass with me, but what you see in the end is some pattern like this, which sort of looks like a mess, but you notice that there's certain dark spots and there's brighter spots. Right? And the dark spots are where all the different paths that the photon could take have suffered destructive interference. So some had positive amplitudes, some had negative amplitudes, they canceled each other out. Okay, the bright spots are where the different paths enjoyed constructive interference, right? And exactly the same is true with all the possible outcomes of our random circuit sampling experiment. It's just that this is happening in a much, much higher dimensional space. And therefore harder to simulate with a classical computer, or so we hope. Okay, so, what we do, well, we do kind of the thing that we know how to do in theoretical computer science, which is to give a hardness reduction. Okay, so we give an admittedly strong hardness assumption. Okay, but, an assumption that does not itself say anything about the hardness of sampling problems, right, which talks only about the average case hardness of a more conventional problem with a definite right answer. Okay, what our assumption says is that there is no polynomial time classical algorithm A, which given as input a random quantum circuit C, from our relevant ensemble with n qubits and with m quantum gates, where m is large compared to n, and this is actually important for reasons we'll see, then the probability over C that our algorithm guesses whether a given amplitude, say, is greater than or less than the median of all 2 to the n amplitudes is only like a half plus some negligible bias of the form 2 to the minus n. Okay? This assumption that you can only do 2 to the minus n better than random guessing is what makes this assumption so strong. Okay, and just to underscore that, there is a polynomial time classical algorithm that would guess whether a given amplitude is greater than or less than the median with this bias over random guessing. 1 over exponential in m, where m is the number of gates in your circuit. Okay? And the way that algorithm works is simply to write the amplitude in question as a sum of exponential and m different contributions, what the physicists would call a Feynman sum, and then just sample some random terms from that sum. Right? It's a very poor approximation algorithm, because of all the cancellations, but it achieves this bias. Okay? So this is why we had assumed that m is large compared to n. Okay, which, I think would be satisfied in practice. Okay, and then we prove a theorem that says if you grant this strong hardness assumption, then actually not only is it hard to sample from, the output distribution of our quantum circuit, not only is it hard to do that approximately, but it is hard to do anything that solves the Hogg problem with a classical computer. Okay, even if that thing, deviated from sampling from the correct distribution. Okay, so that's, the theorem, and the proof is, well, as you'd expect, you sort of assume that that you do have a fast classical algorithm to solve the Hogg problem, and then we show how we could use that to refute the strong hardness assumption. Okay, and I won't go through the whole proof. But, well, it's not a huge proof. It fits on one slide, okay? But the basic idea of it is just, you can run your assumed classical algorithm for Hogg and see whether it ever outputs, the particular output that you care about, right? Since there are 2 to the n possible outputs, the probability, that all have comparable probabilities, the probability that it does so will be very small in any case. Okay, but, if it does output your string, then you can guess that your string probably had a larger than average probability, right? And that's enough to give you a 2 to the minus n bias over random guessing, which would, is not much, but is enough to refute the strong hardness assumption. Okay, of course we would like hardness of random circuit sampling based on a weaker complexity assumption. So recently there was a big progress on this by these authors. What they've shown is that the problem of calculating a random output amplitude for a random quantum circuit is sharp P complete, right? Which is, if you could show that approximating it was also sharp P complete, then we would then get that even approximate random quantum circuit sampling must be hard for a classical computer unless the polynomial hierarchy collapses. Okay, so there's one final step to sort of, that in classical complexity that would need to be finished to sort of show hardness based on the polynomial hierarchy being infinite. But the situation with random quantum circuit sampling is now basically equivalent to what Arkhipov and I were able to do 7 years ago in the case of boson sampling. Okay, we did that by exploiting special properties of the permanent function of a matrix, which arises in quantum optics. What these authors have now shown is that our use of the permanent was not actually needed. One can even make these arguments with completely arbitrary quantum circuits. Okay, so now, let me discuss the question, well, what are the best classical algorithms to simulate a quantum circuit? Right? We should at least make a good faith effort to refute our own hardness assumption, right? Okay, now, of course, this has been very well studied, but Luigi and I sort of made an observation about it that I think has not been made before. And this observation has actually recently become very important for the people, for the groups who are doing classical simulations of large quantum circuits with like 50 or 60 qubits, in order to try to chart out some of the territory for the quantum supremacy experiments, right? And understand, how hard things are going to be to simulate. Okay, so here's the observation. Let's say that you're given a general quantum circuit with n qubits and with m 2-qubit gates. Well then, how should you simulate it with your classical computer, right? It's going to take exponential time by any known method, because of the exponentiality of quantum states, the fundamental reason why we were interested in this whole subject in the first place, right? But there are two completely different exponential time algorithms that have completely different properties from each other, okay? The first is what I'm going to call the Schrodinger algorithm. There's Schrodinger, known as cat, okay? And this would simply be to store the entire vector of quantum amplitudes, so the entire wave function, in your classical computer's memory. Okay, and once, if you've got enough memory to do that, well then simulating a quantum computer is a simple matter of doing a bunch of matrix vector multiplications, right? Quantum mechanics is when you come down to it, is just linear algebra. Okay, just linear algebra over complex numbers. Okay, so you can just simulate that, and you'll need 2 to the n memory. This is what is often prohibitive in practice, but also only quote unquote 2 to the n time. Okay, it's feasible with, let's say, 40 qubits and 1,000 gates if you've got some terabytes of RAM. Okay, but then with 50, 60 qubits, you may already run out of memory. Okay? The second approach is what I'll call the Feynman approach. Okay? And this is to just take the specific amplitude you care about and represent it as a sum of exponentially many contributions. Okay? And you can then just calculate that sum, just sum up all the terms, reusing the same memory each time, right? Analogous to what the particle physicists do when they calculate the amplitude of a Feynman diagram. Okay, this is how one proves that BQP is contained in P space, in polynomial memory, for example. Okay, this approach uses only a linear amount of RAM, but the amount of time it uses is exponential in m, the number of gates. which in practice could be much, much larger than the number of qubits, and which could make this, even if you're Google, you're not going to be able to do 4 to the 1,000. Why? Because it's more than a Google. Okay. Okay. So then we raised the, I guess obvious question, although, for some reason it had not been asked, of, can one get the best of both worlds here? That is there an algorithm to simulate arbitrary quantum circuits which uses polynomial memory, but also time that is merely exponential in n? Okay? And we observed that actually such an algorithm almost exists. Okay? Namely, there is an algorithm that uses only linear memory and time, which goes like the depth of the circuit to the power of n, the number of qubits. Okay? So it's not quite 2 to the n, but it's depth to the n, right? Or 2 to the n times log the depth. Okay? And for any of you who have studied classical complexity theory, if you ever learned Savage's theorem, which says that p-space equals non-deterministic p-space, the proof of this is basically Savage's theorem, right? It is a recursive divide and conquer algorithm, okay, where you take the quantum circuit that you want to simulate, you take the amplitude that you're interested in, which can be, I'm using the physicist notation here, but this is just the notation for vectors and inner products, okay? This is a matrix, these are 2 vectors, right? This means just like x transpose times c times y, which is a scalar, okay? And, you can take that scalar that you want, and you can write it as a sum over all z of, let's say, x c1z times z c2y, where c1 and c2 are 2 halves, 2 equal-sized pieces into which you have cut your circuit. Okay? And then, well, why does that help you? Right? Well, now I can do this sum, and whenever I need to evaluate these terms in it, I can just recurse. And I can take my halves of the circuit and cut them into halves, and so on, right, until I've gotten down to layers of depth 1, where I can just calculate it classically. Okay? And so then I basically just solve a recurrence relation, and I get that running time. And then we show how by exploiting the fact that the Google circuit has a nearest neighbor architecture, one can even do somewhat better than this. But the point I want to make is that even this algorithm still fails to falsify our strong hardness assumption. Okay, why? Well, because in order to falsify the SHA, what you seem to need would be like a guessing algorithm that would run in, like, let's say, if I could just write my amplitude as a sum of 2 to the n terms, right? And then I could just sample some random terms in that sum, and that would falsify the hardness. Okay, but in this case, in order to get this running time we wanted, we had to write our amplitude in a more complicated way, as a sum of products, of sums of products, and so forth. Okay, and that representation doesn't seem to lead to a guessing algorithm that would falsify our SHA. So I think it's a great topic for further research. Okay, and then you have to, of course, when it comes down to an experiment, you have to worry about the effects of errors. You have to worry about, verification, right? So, by, using our recursive approach, there's a group from IBM and another group from Alibaba, and I think Google has now done this too, and they've shown how in some cases they can even take circuits of up to about 70 qubits and just barely simulate them classically, okay? Using our approach. Now as I explained earlier, that certainly does not refute the goal of getting quantum supremacy with 70 qubits, as some popular articles incorrectly said. Okay, on the contrary, you better be able to simulate 70 qubits with your classical computer, because that's the only way you're going to be able to verify the results. But it better be slow, and indeed it is slow. Okay. All right. So but now having said all of this, right? You may say, well, we'll just if the experiment works correctly, then the outputs are just a sample. Well, not exactly from the uniform distribution, but from some distribution whose entropy is n minus a constant, right? For some distribution that is very, very close to being uniform, right? And in fact, it takes this super hard classical computation even to see that the distribution is different from uniform, right? So, you know, all you're seeing is basically a bunch of completely random looking bits, right? So that's obviously completely useless to anyone, right? Now, the point of the new work that I've been doing in the last 6 months or so is to realize, hey, you know, actually there are people who want random bits, right? Random bits are useful to some people, especially if you can know that they are random. Okay, so certainly, you know, having secret random bits is fundamental to doing, you know, almost any sort of cryptography, right? You need either, you know, for a public key, for a private key, you need, you know, either random bits that are known only to you or known only to you and to the person you're communicating with. But also, there are also many uses for random bits that would be publicly announced to the world. Okay, most obviously for a lottery, right? Or also for choosing which precincts should be audited in an election, right? Everyone has to agree that the choices were made randomly. Setting the parameters for crypto systems. If you want something trendier, cryptocurrencies. Okay, there are these new proof-of-stake cryptocurrencies which try to get the advantages of Bitcoin, but without having to spend 1% of the world's electricity or whatever it is in inverting a hash function. Okay, and the way that they do it is that everyone who owns coins has the right, essentially, to enter into a lottery to add new blocks onto the blockchain, which they then get paid for, okay? But then, you know, lotteries have to be constantly conducted, and everyone has to agree, you know, be able to believe that they're being conducted fairly. So you need lots of public, verifiable, random bits, okay? Now, you know, this is a known problem. NIST in the US actually has something called the randomness beacon, which every minute releases 512 fresh random bits to the world. And, you know, and partly using quantum mechanical sources to do it, okay? But now the question is, well, how can you trust that, right? I mean, in fact, we learned from Snowden a few years ago that one of NIST's pseudo-random number standards was backdoored by the NSA, okay? So, you know, but even, you know, assuming that, you know, that's not the case for the randomness beacon, well, still, how would you know it? Okay, so, you know, now you may say, you know, well, once we have quantum mechanics, it is trivial to get random bits, right? It's sort of baked into the theory, right? In fact, I could draw, this is maybe the simplest quantum circuit that it is possible to draw. This Hadamard is a 1-qubit quantum gate that takes a qubit and puts it into an equal, let's say that's initially 0, and puts it into an equal superposition of the 0 and 1 states. If you then measure the qubit, you see 0 half the time and 1 half the time, right? This is just quantum mechanics 101, right? It's whatever, God plays dice with the universe, okay? Accept it, okay? But you know, even, you know, assuming you believe, you know, quantum mechanics as you should, well, still, how do you know that this, you know, this circuit is actually what is inside your random number generating box, right? Or if you're getting random bits over the internet, how do you know that NIST, or the party on the other end, is really using this box? Okay, so that is the problem that we're trying to solve here. Okay. So, as I mentioned, there was a beautiful sequence of works over the past decade that gave an earlier quantum mechanical solution to this problem. And that solution was to use the famous Bell inequality, which is this you know, inequality involving measurements on two separated but entangled particles, right, where Bell proved in the 1960s that the statistics of the outcomes of these measurements that was predicted by quantum mechanics could not be reproduced by any classical, you know, local theory. Okay, so Einstein was just wrong about it, right? You know, but because, you know, the experiment was actually done by the 1980s and the results are 100% consistent with quantum mechanics. There were still some loopholes in the experiment, but just 2 years ago, finally the first experiments were done that close all of the loopholes. And so now, very recent.
No, even more. There was some loopholes.
Well, I mean, the first paper that they got out had only 2 sigma confidence. That's because they were just rushing to get the paper out and beat the other groups, okay? But now it's been verified at like 20 sigma or something, okay? So I think, I think it's safe to say, yeah, Einstein was wrong. There's not local hidden variables. Entanglement is a real phenomenon in the universe. And if you doubted that 2 years ago, well, you shouldn't doubt it today, okay? So, okay, but now what people started realizing a decade ago is that the Bell inequality does not only prove the reality of quantum entanglement in our universe, it does something more, which is that if the test succeeds, like your experiment violates the inequality, then you know that the outcomes of the measurements must have had some entropy in them. They must have had some randomness in them, unless there was faster than light communication between, Alice and Bob, between the 2 separated parties, okay? Because, if there wasn't, then the experiment would lead to a means of faster than light communication. Okay, and incredibly, this argument does not even require you to know or believe quantum mechanics, right? It is more basic than that. Okay, so people realized, hey, this is actually useful, or could be. We could use this to get a source of sort of, Einstein-certified randomness, as my Umesh Vazirani, who was my advisor at Berkeley, coined it. Okay, so, but there was still a problem, which is that in order to do these experiments in the first place, you need random bits to generate the challenges to send to Alice and Bob. Okay, so for a while it seemed like these present-day fusion reactors, right, where, yes, they generate energy, but it takes more energy to run them than what they generate, right? It looked like you would need more random bits to feed in than you would actually get out from this process. Okay, but Kolbeck and Renner gave the first protocol where, by being more clever about how you generate the challenges to Alice and Bob, you could get a linear expansion in the amount of seed randomness that you started with. Then Peronio et al. Showed how to get a quadratic expansion. These guys showed how to get an exponential expansion. And these guys showed how, from a fixed size random seed, like we estimated it as 10,000 random bits, but it's probably actually less than that in practice, you could then get an unlimited further number of random bits using this sort of protocol. Okay, so an upside, this does not need a quantum computer, needs only current technology, meaning from 2 years ago, loophole-free Bell experiments. Okay, but the problem with it is this doesn't seem to work well for getting public random bits over the internet. Because, NIST may tell you that, that they're doing this, right? In fact, I think they are now, as of very recently, using a Bell inequality to help generate their random bits. But in fact, their devices are not far enough separated to evade these loopholes, okay? But even if they were far enough separated, well, how would you know that, right? You're some, user in Kazakhstan or whatever, right? How do you know what's going on in NIST's lab? Okay, so it would be better to just get certified randomness from a single quantum device. And this is what our new proposal is to do. And it is to use, in place of the Bell inequality, to use just a single quantum computer, which could be a near-term 50 to 70 qubit quantum computer, just enough to demonstrate quantum supremacy, okay? And the basic idea of the protocol is that you have a classical client that starts with a small random seed. It then pseudo-randomly expands that seed into a set of challenge circuits, which it then sends to the quantum computer one by one. And each time, it challenges the quantum computer to sample from the output distribution of that quantum circuit. And it demands back a response within a very short time, like let's say half a second or something, okay? And it collects these responses. It then, using its seed, picks a small number, representative sample of the challenges, and it checks whether the quantum computer was actually solving the Hogg problem that I told you about before. Okay? And then, if the Hogg problem is being solved, then we prove a theorem that says, well, look, a quantum computer could solve the Hogg problem quickly, but it can only do it by under some reasonable complexity assumptions by sampling from a distribution that has a lot of entropy. There is no deterministic fast way to solve the Hogg problem, even using a quantum computer under some plausible complexity assumptions. Okay? So if you see that Hogg is being solved, then you are basically confident, modulo your complexity assumptions, that there must be real randomness in what this device is sending you. And that's even if the quantum computer is owned by the NSA, right? Or, if it's been backdoored by your adversary. Okay? So this requires just a single device. It is ideally suited to what are called noisy intermediate scale quantum devices, the ones we hope to have in the next few years. In fact, with this sort of protocol, even if you had 1,000 qubits, you couldn't really use them because you wouldn't know how to verify the results. Okay, so it's sort of optimized for the 70-qubit quantum computers that we're hoping to have in the next few years. Okay, it does require computational hardness assumptions. It does require initial seed randomness. The verification takes exponential classical time, but that's just the same issue as with any of these quantum supremacy experiments. Okay, so you could use it for private randomness. You could use it for public, if you own the quantum computer yourself. Or if you're connecting to one to the internet, then you can use it for public randomness. I do not recommend using it for private randomness in that case, if you're downloading the bits from Google, okay? It does, you may say if it requires pseudo-random challenges, then what's the point? Why not just use your pseudo-random bits and be done with it, okay? Well, one answer to that is that you get this forward secrecy, in the sense that even if the pseudo-random generator were to be broken in the future, as long as it's not broken now, the random bits that you get are still secure, right? You get some other nice cryptographic advantages, like freshness. You know that the random bits were not known to anyone earlier, not even to the quantum computer itself, which can be useful for time stamping. Okay, so I had, here I just go over the protocol in more detail. I'm not going to do that because I'm running out of time. Let me just say the last step of the protocol is that you collect together all of the outputs of your of the quantum computer, and if they pass the verification, you then feed them into a well-known tool from classical computer science, which is called a seeded randomness extractor. And what that can do is, again, using your random seed, it can take this large string that has some entropy in it, but which is not perfectly random, and it can extract from it a long string that is nearly perfectly random. Okay, and that's known how to do. So we just use that, off the shelf. Okay, and then we prove a theorem that basically says that under some suitable hardness assumptions, this protocol, if the verification test passes with high probability, then there must be a large amount of entropy being generated in each round. Technically, what computer scientists call min entropy. Okay? The hard part is to show that the min entropy accumulates from one round to the next, that the rounds are not somehow conspiratorially correlated with each other, even though the quantum computer may have a memory and also be adversarial. Okay. There's in some beautiful independent work, there's a completely different approach to this problem by these authors. I'm not going to really have time to talk about it, but what they do, they also give a protocol for generating certified random bits using a quantum computer. Okay? Their protocol is based on the hardness of lattice-based cryptography, the security of lattice-based crypto systems against quantum attack, which is something that many of us believe today, and which is more standard than my assumptions. Okay? They also get an enormous theoretical advantage over my scheme, which is that they can give a polynomial time classical algorithm to verify the outputs of their protocol. Okay? I can't do that with my way of doing it. The advantage of my scheme is simply, well, there is some hope of implementing it in the next few years. Okay, theirs seems to, require like 1,000 qubits at a bare minimum to get any sort of security. And by then you're talking quantum error correction, and you're talking at least a decade in the future, maybe probably more. Okay, so there's many exciting future directions, like can we get quantum supremacy under more standard and less boutique complexity assumptions? Can we get polytime classical verification and near-term implementability of one of these random number schemes at the same time? Could we get more and more certified random bits by sampling with the same circuit over and over? If we could do that, that would enormously improve the bit rate of the scheme, but I don't know how to prove that it's secure. Okay? And then, one could also ask for stronger forms of security. Okay, so conclusions. We may be close to roughly 70-qubit quantum supremacy experiments. We can say non-trivial things about the hardness of simulating these experiments, but we'd like to say more. I think that certified randomness generation may be interesting, not as like the most important application for humanity, but as maybe the most plausible application that has been found for very near-term quantum computers, right? It's not clear what else you're going to do with a 70-qubit quantum computer that is useful to anyone, okay? And that's why Google is excited about this, basically, right? This application requires sampling problems. Problems with definite answers, like factoring, are useless. Not only can we do it with 70 qubits, we don't even want more. Okay, so with this application, it feels to me like all the weaknesses of these sampling-based quantum supremacy experiments have somehow become strengths. Okay, thanks.